Good morning. Thank you for the introduction. So I would like to briefly introduce our department with respect to possible collaboration in space technologies. I will briefly mention our activities related to space research in 4 different areas, and then I will also briefly mention our laboratories at our disposal. So in the field of radio wave propagation, we have quite a long history of collaboration with European Space Agency in modeling for interference and frequency coordination analysis. For example, in the currently running contract, we are focused on risks of interference to space exploration missions from 5G networks in millimeter frequency band. The illustration in this slide are from our earlier contract, under which we conducted quite challenging experiments, for example, to verify diffraction models or to collect long-term statistics of propagation enhancements in the atmosphere. Completely different experiments were carried out for mobile satellite communication scenarios, where we have a small remote control airship and as a pseudo satellite, and then monitor effects of environment on the transmission at multiple frequencies. Illustration on the left, it's for signal penetration into buildings, and on the right, it's measurement of vegetation shadowing. And of course, always the goal was to derive relevant empirical propagation models. Another area our group of computational electromagnetics is involved in is a search for fundamental bounds of electromagnetic structures. For example, suppose we have a well-defined limited space on a satellite in which we want to place a sensor of an antenna. And the challenge now is to find theoretically achievable limits of relevant parameters. This is not a trivial task. For example, on the right, you can see fundamental bounds of antenna array of given dimensions in terms of directivity, frequency bandwidth, and radiation efficiency. And you can nicely see how these parameters conflict with each other, and of course how then such an analysis would be extremely useful for system design and of course design of the antenna in question. I have 3 examples of optimal designs which tries to converge to these theoretical limits. In the first one you see a dielectric structure that surrounds a center space and makes it invisible. There is a plane wave propagating from the left, and you see it continues on the right again as a plane wave. So this dielectric shell ensures that, for example, a sensor placed inside does not electromagnetically affect its surrounding. In this graph in red, you can see dependence of fundamental bound of radiation efficiency on focal length of a dielectric lens of given dimensions. For example, it can be placed in front of a sensor when we try to achieve the best possible efficiency for the given focal length. The dashed line then represents outputs of our automated design algorithm. For 3 realizations marked ABC are also, for them you can also see in blue the structure of the lens. And finally, the third example is again focused on optimizing the use of space. Here we consider antenna elements distributed over a sphere of, again, given dimensions and electrical properties. And we ask for fundamental bounds of maximum gain of such an antenna. So here you can see optimal radiation patterns for 5 different resistivities of the sphere and 2 different dimensions of the sphere. Another area, we have a many years of experience with actual designing the antennas for various space applications. For this presentation, we selected 4 examples. On top left figure, you can see special reflector feeds, where there is an emphasis of maximizing antenna gain to noise temperature ratio. We are able to design and fabricate multi-band feeds, and we can also combine different polarizations. Top right, there is a short backfire antenna at 2.4 gigahertz. It's for the uplink to the geostationary transponder. What is unique about it is that it is the use of meta-surface, which enables transformation of polarization from linear to circular. We are also interested in designing antenna arrays in microwave band. Bottom left picture shows 3-element array with shared aperture. And finally, the last example, bottom right, it's so-called orthomode transducer, which allows to combine 2 orthogonal polarizations from 2 ports into a horn antenna. This one is optimized for 26 to 40 gigahertz frequency band, and the port crosstalk is as low as -50 dB. And the 4th area, our optical group, is involved within a large international consortium in the application where there is a satellite network used for quantum key distribution. There is an experiment in the preparation phase when we want to verify quantum key transmission over free space optics using polarization entangled photons. The plan also is to test the effects on, to analyze the effects on atmosphere of this transmission. For this kind of testing, we have a turbulent chamber where we can measure impact of turbulence, fog, scattering in laboratory environment. This illustration is from diversity testing, specifically measuring the system parameters of the whole transmission for 2 parallel laser beams with differently correlated turbulence. Now I have a few slides about our laboratories and key equipment. I think who is interested, you can, if you are interested, you can look at them offline, or you can look at our web. Here I will just make a short overview. We have a shielded anechoic antenna chamber with number of measurement method implemented for both antenna and EMC measurements. Our upper frequency limit is 110 gigahertz. It is given by the equipment. The same limit is for our vector measurements in our microwave and millimeter frequency, millimeter wave laboratory. And finally, we also have a special laboratory dedicated to free space and fiber optics. I have to also mention that we maintain licenses of quite a number of powerful commercial packages implementing various numerical methods, mostly for solving electromagnetic fields. And of course, we have some in-house developed codes as well. So it brings me to a summary. So these are the topics you would like to find partners to collaborate with. And these are the persons responsible for the 4 relevant areas. You can contact them directly, and they are also co-authors of this presentation. Thank you very much.
Thank you very much.